All right, so this video I'm just gonna make up some problems, and we're gonna look at first fundamental theorem, second fundamental theorem, basically the same thing, just thinking about it in a different way, and do some computation. So we're not gonna talk much about why these things work, but just simply look at some examples. So let's look at an example 1. Say we have the integral from 1 to 3 of sine of 3x dx. So, first fundamental theorem says the area under this function is given by the change in its antiderivative. So therefore, we need to find the antiderivative of sine of 3x. Well, that's negative cosine of 3x divided by 3. That's a very simple u substitution problem, technically. Remember, if you took the derivative of negative cosine of 3x, you would get sine of 3x times 3, so that's why you have to divide by 3 so that we don't end up with that extra 3. We're going to evaluate that between 1 and 3. That's what this means. And so that is going to give me negative cosine of 9 divided by 3 minus a negative cosine of 3 divided by 3. We could rewrite this if we wanted to. This is going to become plus as 1/3 times cosine 3 minus cosine 9. Okay? Let's say we have an example number 2. Say we've got the integral from 0 to 5 of square root x minus 2x squared plus 1 over x dx. Again, first fundamental theorem says find the antiderivative, plug in upper limit, lower limit. So we should get x to the 3/2 times 2/3. This is x to the 1/2, right? So if you add 1 to that and then divide by that, you've got x to the 3/2 divided by 3/2, but that's 2/3 x to the 3/2. Then minus 2x cubed divided by 3, and then plus ln absolute x. And this is going to be not from 0 to 5, because that's not even defined there, and that's too complicated for this example. So we'll go from 1 to 5. Now we simply need to plug in 5 and plug in 1. So that should be 2/3 times 5 to the 3/2 minus 2/3 times 5 cubed plus ln of 5 minus, in parentheses, 2/3 minus 2/3 plus ln of 1. This whole thing is going to go to 0, so we could actually just get rid of that. When we plug in 1, all that stuff goes to 0. So that is the first fundamental theorem of calculus, simply finding an antiderivative, plugging in the top limit, plugging in the bottom limit. Now the second fundamental theorem is actually easier in some ways, or maybe always, I don't know. And this is when we have the derivative of an integral from some constant to a variable of some function in here. Let's say it's sine squared of t dt. Well, basically what the second fundamental says is if you take the rate of change of an area function, you just get the function you're finding the area underneath, which actually makes a lot of sense when you think about it. If a function's going up quickly, your area is going to increase quickly. If your function's negative, your area is going to decrease. So it makes a lot of sense. And basically what we know is this just becomes sine squared of x. Example 4 would be, say, the derivative from 200 or 2000 to x of cosine t plus 5t squared minus 7 ln t or something dt. Again, we're going up the stairs, integrating, plugging in x, plugging in 2000. Then we're taking a derivative, so everything that we plug 2000 in is going to 0, so it doesn't matter. And we just basically get cosine of x plus 5x squared minus 7 ln x. So remember, if you're taking the derivative of an integral, you should not be integrating at all. You should not be finding an antiderivative. That is this derivative. If instead of having an upper limit of x, we have some function, say 20 or negative 20, let's say, to sine of x plus 5, and let's make this t squared dt. Then we play a similar role. We plug this function in, but then we multiply by the derivative of this function, because in a sense, if we were to show the steps of this, we would find, right, well, we know already that we just plug this in, and we get sine of x plus 5 all squared, but then we have to multiply by cosine x. But if we were to show the actual steps of this, we would get the derivative of, now let's use the first fundamental theorem here and say, well, that's going to be t cubed over 3 evaluated between negative 20 and sine x plus 5. Then we would get the derivative of sine x plus 5 cubed over 3 plus some constant c, because we're going to plug in negative 20 and get some constant. Then when you take the derivative of this, you'll multiply by 3. The 3's will divide. You'll get sine x plus 5 squared, but then you'll have to multiply by cosine x. So we don't want to take all those steps. We want to just remember that we can just simply plug this in to t squared and then multiply by its derivative, cosine x. And again, that's if you have a derivative of an integral function. Okay, let's look at just a couple other things here. If you have the integral from x to a, and you're taking the derivative of, say, oh, let's call it tangent of ln of t dt, then you can just reverse the limits, right, to get it into this form. Or you don't even have to. You can just remember, oh, this is going to be negative, because now I'm doing the constant minus the function instead of the function minus the constant. So this is just going to give me the opposite side, negative tangent of ln of x. If I have, say, the derivative of a function from negative 2x to 5x squared of 3t squared plus 5t minus arctangent t dt, well, then I'd be plugging in this one, then plugging in this one, but I'd be subtracting them. So basically, you plug in the top one, multiply by its derivative, plug in the bottom one, multiply by its derivative, and subtract the 2. So you should have 3 times 5x squared squared plus 5 times 5x squared minus arctangent of 5x squared, all times the derivative of 5x squared, which is 10x. And then you should plug in negative 2x minus 3 times negative 2x squared plus 5 times negative 2x minus arctangent of negative 2x, all times negative 2, which is the derivative of negative 2x. And that, again, really is because you're thinking about rewriting this as negative 2x to a plus a to 5x squared. And so this one is going to be negative, and this one's just going to be normal. And so that's sort of how the first fundamental and second fundamental theorems work computation-wise.